All right, welcome back to the deep dive. Today we're looking at something super cool, at least for all you medical imaging and machine learning folks out there.
Yeah, I mean, this is right up our alley, right? Like the intersection of AI and healthcare, specifically in cardiology.
Exactly, it's cardiology and AI today. And you know those ultrasound images? The ones they use to see what's going on with your heart?
Oh yeah, echocardiograms. Those are crucial for diagnosing all sorts of heart conditions.
Well, there's this new paper we're diving into, and they've come up with this open dataset and AI framework called KACPUZ.
KACPUZ, huh? Okay, I'm intrigued.
Yeah, and get this. They're using deep transfer learning to make the analysis of these ultrasound images automatic. So basically, teaching AI to understand and assess these crucial images.
Interesting. So it's not just about recognizing what's in the image, but also figuring out the quality of the image itself?
That's exactly it. Automating both the identification and the quality assessment, which is honestly a pretty big deal if you think about how much time and effort it takes for experts to do that manually.
Huge time saver, for sure. And you know, there's a real shortage of skilled technicians in many places. So this kind of automation could have a real impact on healthcare access and efficiency.
Right, think about it. Faster analysis, maybe fewer errors, and potentially helping to address those workforce shortages. It's like a triple win.
Yeah, this is definitely worth a closer look.
Okay, so let's jump into this CACTUS paper, shall we?
Let's do it.
So the researchers start by pointing out some big limitations they've found in the existing cardiac ultrasound data sets.
Okay, what kind of limitations are we talking about?
Well, for one thing, a lot of these data sets don't include enough variety in the types of heart views they cover.
Right, different angles, different structures. You need that variety to train a really good model.
Absolutely.
Yeah.
But maybe even more important is that they often lack any kind of standardized grading of the image quality.
So it's not just about having enough images, but also about knowing how good those images actually are.
Precisely. You need that quality assessment to teach the AI to differentiate between a good image and a bad one. So what these researchers did is they created this new data set, the CACTUS data set, which they made publicly available.
Publicly available, that's awesome. Good for the research community.
Oh, it gets better. They had experts meticulously grade each image for quality.
Oh, wow. Okay, so that's where the graded part comes in.
Exactly. And then, of course, they built this whole AI framework designed specifically to work with this graded data set.
That makes sense. You need a framework that can leverage that quality information to train the model properly.
And, you know, this whole thing really speaks to the problem of data scarcity in machine learning.
Oh, yeah, absolutely. We talk about this all the time on the show, right?
All the time. You need large, high-quality data sets to train these powerful AI models. And in specialized areas like medical imaging, getting those data sets can be a real hurdle. So creating this CACTUS data set, it's like they're directly attacking that problem.
Yeah, it's like laying the groundwork for more advanced AI development in cardiac imaging, a solid foundation, which is so important.
It is. Okay, so before we go too deep into the technical stuff, let's just take a second to appreciate how challenging it is to work with these ultrasound images, even for humans, for experts.
Right. I mean, imagine you're trying to classify those different views of the heart, and then on top of that, you have to judge the quality of those images.
Exactly. You're dealing with variations in each person's heart anatomy, the precise angle of the ultrasound probe, and then all these weird image artifacts like speckle and noise.
Oh, yeah, all those things that can mess with the clarity of the image and obscure details.
Right. It's not easy at all. So if we can automate that process reliably, it could really improve things.
Absolutely. Faster analysis, fewer potential errors.
But also think about consistency.
Oh, that's a good point. You know, even the best cardiologists, even with all their training and experience, they can still have some subjectivity.
It's true. And with so many images to review, it can be hard to maintain perfect consistency.
But AI, on the other hand, it could potentially provide more consistent, objective assessments. No matter how many images you throw at it, it applies the same criteria.
Exactly. And that consistency could lead to more reliable diagnoses and ultimately better care for patients.
So it's not just about speed and efficiency, but also about quality and accuracy.
Absolutely. Okay, so we've talked about the challenges, the need for a good data set. Let's dive into this CACTUS data set itself. What makes it so special, so valuable?
Well, first off, the name, CACTUS, it stands for Cardiac Assessment and Classification of Ultrasound.
Okay, pretty straightforward.
Yeah, they kept it nice and clear. But here's the big thing. It's the first open and graded data set for cardiac ultrasound.
We touched on that earlier, but yeah, that grading seems to be the key here.
It is. It's really what sets it apart. So they used a CAE Blue Phantom for this.
A phantom.
Yeah, it's basically a model that mimics the anatomy and the acoustic properties of the human heart. It's used to create standardized ultrasound images.
Oh, okay. So it's a controlled way to generate the data.
Exactly. And they captured all sorts of clinically important heart views.
Like the standard views, the ones you see in the textbooks.
Yeah, they have those.
Yeah.
The apical four-chamber, subcostal four-chamber, parasternal long axis.
The classics.
Right, the classics. But they also included some views that go beyond the usual suspects.
Oh, interesting. Like what?
Well, they specifically focused on the aortic and mitral valves, so they included 2 parasternal short-axis views, one for each valve.
So they're really trying to cover a wider range of what you might see in clinical practice.
Exactly. They're not just sticking to the basics. They're trying to be more comprehensive.
That's great for training a more robust AI, right?
Oh, absolutely. The more variety you have in the training data, the better the model can generalize to real-world scenarios. And there's another clever thing they did with the data set.
Okay, all ears.
They added a whole category of random ultrasound images.
Random. Like, what do you mean?
Images that are not of the heart at all, just random stuff.
Why would they do that? Seems counterintuitive.
It's actually really smart. They graded all these random images as 0.
Okay, I'm starting to see where you're going with this.
It's all about teaching the AI what not to pay attention to.
Like distinguishing between a real cardiac view and something that's just noise or irrelevant.
Exactly. That's a crucial skill for any AI that's going to be used in a real clinical setting.
Yeah, you don't want to getting distracted by something that's not a heart.
Right. And this is a great way to train the AI to focus on what's important.
Okay, that makes a lot of sense.
Wow.
So we've talked about the different views, the random images. Now let's get into the nitty-gritty of that quality grading. How do they actually go about doing that?
All right. So they brought in these cardiac imaging experts.
Real pros.
Yeah, the best of the best. And these experts had to carefully look at each and every image and give it a quality score.
On a scale of 1 to 10, right?
That's right. 1 being poor quality and 10 being excellent.
But it wasn't just like a gut feeling, right? They had specific criteria.
Oh, yeah, absolutely. They had a whole detailed schema they used.
Break it down for us.
Okay, so they looked at things like the completeness of the anatomical view, basically how much of the heart you could actually see in the image.
Okay, that makes sense.
Right, and then they assessed the clarity of the image, taking into account stuff like noise, artifacts, and whether the technical settings like gain and power were appropriate.
So they were really looking at both the anatomical completeness and the technical quality of the image.
Precisely. And they even had these specific levels within the scale.
Like subcategories.
Yeah, so 0 was for the non-cardiac images, and then levels 1 through 7 to 10 were defined by these specific criteria.
Wow, that's a really fine-grained grading system.
It is, and that's great for the AI because it gives it a lot of nuanced information to learn from.
So it's not just good or bad, it's good because of this or bad because of that.
Exactly. It allows the AI to understand the subtleties of image quality. And all in all, the data set ended up with over 37,000 images.
37,000 images, that's a lot of data.
It is. It's a solid foundation for training a really good model. And here's another thing I appreciated about this paper. They were super transparent about their experimental setup.
Okay, good transparency is always a plus in research.
Right. They told us exactly which ultrasound equipment they used.
Which was?
A GE M4S matrix probe and a GE Healthcare Vivid Q US machine.
Okay, so they specified the models.
Yeah, and they even provided the ranges for all the different imaging parameters they varied during the data acquisition.
Like the depth, the gain, the frequency.
Bunch of that. They laid it all out there.
That's great for reproducibility, right?
Yeah.
Other researchers can try to replicate their results.
Exactly. And it also helps anyone who wants to use the data set to understand how it was created and what those images actually represent.
Excellent. And just to remind everyone, the link to this data set is available in the paper.
Yeah, go check it out. It's a valuable resource for the whole research community.
All right, so we've got this amazing data set. Now comes the fun part. Building an AI that can actually make use of it. How did they approach that?
Okay, so they developed this AI framework with 2 main components.
2 components. What are they responsible for?
One is for classifying the heart view, figuring out which specific view the image shows.
Okay, that's one part. And the other?
The other is for grading the image quality, basically taking all that expert grading data and teaching the AI to do the same thing.
So one component figures out what, and the other figures out how good.
Precisely. And they used a convolutional neural network, or CNN, for this. Specifically, they started with a ResNet 18 architecture.
ResNet 18, that's a pretty standard choice for image analysis, right?
Yeah, it's a solid architecture, well established, known to be effective for learning those hierarchical features in images. But here's where things get really interesting.
Okay, hit me with it.
They use transfer learning.
Ah, transfer learning. So instead of training two separate models, one for each task, they're sharing some of that learned knowledge.
Exactly. They built this common feature extractor, which is like the part of the AI that learns to identify the basic visual patterns in the images.
Okay, so it's learning the fundamentals of what a heart looks like in ultrasound images.
Exactly. And then they attach two separate heads to this shared feature extractor.
Two heads, like a two-headed monster.
Kind of, yeah. One head is for classification, so figuring out the view, and the other head is for grading the quality.
So it's like they're taking this shared knowledge, this foundation, and then applying it to two different tasks.
That's the beauty of transfer learning.
So what are the advantages of doing it this way? Why not just train two separate models from scratch?
Well, for one thing, it saves a lot of computational resources.
That's always good. Training deep learning models can be really resource intensive.
It can. But by sharing that feature extractor, both tasks can benefit from the learning that happens across the entire data set. They don't have to start from zero each time.
So it's more efficient.
Much more efficient. And often it leads to better performance too, especially when you're dealing with a task where you might not have tons and tons of labeled data.
Right, because it's like the model is getting a head start.
Exactly. It's already learned some useful stuff from the other task. In this case, it's learning about heart anatomy in general, which helps it both identify the specific view and assess the quality of that view.
Makes perfect sense. So how well did this two-headed monster, this dual task framework, perform on the CACTUS dataset?
Drumroll, please.
Give us the numbers.
Okay, so for classifying the different cardiac views, they hit an accuracy of up to 99.43%.
99.43%? That's crazy high.
It is really impressive. And for the image quality grading, they got a mean absolute error of just 0.3067.
0.3067 on that 1 to 10 scale. That's tiny.
It is. It means the AI's grading is very close to the expert grading.
So the initial results suggest that this approach is really working.
It does seem to be working really well, but they didn't stop there. They wanted to make sure this thing is robust.
Okay, how do they test that?
Well, they did a couple of things. First, they fine-tuned the model on a new cardiac view.
A new view, one that wasn't in the original data set.
Exactly. They added the parasternal short axis at the mitral valve level, or PSMV for short.
So they threw a curveball at it, a new challenge.
Yeah, and they wanted to see how quickly the AI could adapt.
Yeah, could it?
It did. They said it converged really quickly and performed well on this new class of images.
That's good news. It means it's not just stuck in its ways. It can learn new things.
Exactly. It's adaptable. And then they did another test. They compared their ResNet 18 with transfer learning to a bunch of other CNN architectures.
Okay, like what?
All the big names. ResNet 50, VGGNet 19, InceptionNet V3, AlexNet.
So they wanted to see how their chosen architecture stacked up against the competition.
Exactly. And the results were really interesting.
Tell us.
Well, when they looked just at the grading task, their ResNet 18 without transfer learning wasn't the absolute top performer.
Okay, so some of the other architectures did slightly better in terms of grading loss.
Yeah, but here's the kicker. When they added transfer learning, their ResNet 18's performance jumped up significantly.
Oh, wow. So transfer learning really gave it an edge.
It did. It even outperformed a multitask learning approach where they trained both classification and grading simultaneously from the beginning.
So the sequential transfer of knowledge from the view classification to the grading task, that was the winning strategy.
It seems so.
That's fascinating. But all these metrics, all these numbers, they only tell part of the story.
True. You need to see how this thing actually works in practice.
Exactly. Did they do any real-world testing?
They did. They had experienced cardiac sonographers use the AI framework during actual real-time scans.
Okay, so they brought in the experts again.
Yeah, and they had them fill out questionnaires about their experience.
What kind of questions?
Things like how responsive the system was, how useful they thought it would be in their workflow, how intuitive the AI's output was.
Just getting a sense of how well it integrated into a real clinical setting.
Exactly. And the overall feedback was positive. They gave it an average score of 8 out of 10.
Not bad at all.
Yeah, not bad. But of course, there were some challenges too.
What kind of challenges?
Well, the experts noted that the AI sometimes had trouble distinguishing between some of the more subtle variations in cardiac views, especially on the phantom.
Okay, so there's still room for improvement, especially when it comes to those tricky cases.
There is. But overall, I think it's pretty encouraging that experienced sonographers found it helpful.
Yeah, that's a good sign.
Yeah.
Now, I know you're big on explainability, so I have to ask. Did the researchers try to understand how the AI was making its decisions?
Oh, absolutely they did. They wouldn't have gotten this published otherwise.
Good point.
Yeah.
So how did they approach the explainability part?
They used GradCam plus PIO. It's an explainable AI or XAI technique that creates these heat maps showing which parts of the image the model is focusing on.
Ah, so you can actually visualize what the AI is paying attention to.
Exactly. And what they found is that the model was indeed focusing on the relevant heart structures.
Okay, so it wasn't just picking up on random noise or artifacts. It was actually looking at the right things.
That's what it seemed like. And that gives you more confidence in the model's reasoning, right? You can see that it's not just spitting out random answers. It's actually basing its decisions on the right information.
Absolutely. It makes the whole system more transparent and trustworthy. Okay, so we've covered a lot of ground here. If you had to sum up the key takeaways from this CACTUS project, what would they be?
All right, let me give you the highlights. First, they created this fantastic CACTUS wall data set, which is a huge contribution.
It's the first publicly available graded data set for cardiac ultrasound, right?
That's right, and that's a big deal for the research community. This data set will hopefully accelerate a lot of future work in this area.
It's like they paved the way for others to build on their work.
Exactly. And the second big takeaway is that they demonstrated this really effective deep learning framework that uses transfer learning for both classifying cardiac views and grading image quality.
Two birds, one stone.
Exactly. And they showed that it can adapt to new cardiac views, which is crucial for real-world applications.
So what's next? What kind of future research do they suggest?
They've got a whole list of exciting directions they want to explore. One is expanding the data set, of course.
Got to keep feeding the AI.
Right, and they want to go beyond the phantom, start incorporating data from actual human hearts.
Okay, that's a big step. Real human hearts, that's where the rubber meets the road.
It is. And it's much more challenging, of course, because there's so much more variability.
Yeah, everyone's heart is different. But that's ultimately the goal, right? To build AI that can work in the real world.
Absolutely. And they're also looking at using AI for more advanced tasks.
Like what?
Like actually quantifying cardiac function.
So not just saying this is a view of the heart or this image is good, but actually measuring things.
Exactly. Measuring things like ejection fraction, valve areas, all those clinically important parameters.
That's really moving beyond just image analysis and into the realm of diagnosis and treatment planning.
It is. And it has the potential to really change how we approach cardiac care.
Absolutely. Anything else on their research agenda?
Yeah, they want to tackle some of the limitations of transfer learning.
Okay, what kind of limitations?
Well, things like negative transfer, where the knowledge from one task actually hurts the performance on the other task.
Ah, so it's not always a win-win.
Right. And there's also the computational cost, which can still be high, even with transfer learning.
So finding ways to make it even more efficient.
Exactly. And they mentioned looking into domain adaptation techniques, which can help make the model more robust to different types of data.
So making it work well, even when the training data and the real world data are a little different.
Precisely. It's all about making the AI as reliable and adaptable as possible.
It's exciting stuff. I mean, this research really feels like it's pushing us closer to a future where AI is a routine part of cardiac care.
It does, doesn't it? Imagine a world where these AI systems are integrated into the ultrasound machines.
Like having an AI assistant right there with the sonographer.
Exactly. And not just interpreting the images after the fact, but actually helping to acquire better images in real time.
Okay, now we're talking. That's next level stuff.
It is. It could really change how cardiac sonography is taught and practiced.
All right, now it's time for our favorite segment. Novel notions. Time to speculate a bit, get those creative juices flowing.
I love this part.
Okay, so based on this CACTUS paper, what's a potential, maybe even a bit out there, extension of this work that you can imagine?
Okay, so building on this idea of AI-assisted image acquisition, imagine a system that goes beyond just flagging bad images.
Okay, so not just saying, nope, try again.
Right. Imagine it actively guides the user towards getting better images in real time.
Oh, like a little AI coach whispering in your ear, a little to the left, a little more pressure.
Exactly. So as the sonographer is doing the scan, the AI is constantly analyzing the incoming data.
And if it sees that the quality isn't good enough, It gives the sonographer feedback right then and there.
Right. Maybe it shows some visual cues on the screen, like arrows indicating which way to move the probe.
Or maybe it changes the color intensity of the image to signal improved clarity.
Yeah, something like that. The goal is to create this real-time feedback loop that helps the sonographer optimize the image quality as they're scanning.
That's a cool idea, like having an AI co-pilot for ultrasound.
Exactly. And think about how valuable this could be for training new sonographers.
Oh yeah, they could learn proper scanning techniques much faster.
Right. And it could also help to reduce variability in image quality between different operators.
So everyone's getting those high-quality images regardless of their experience level.
Precisely. It could really standardize the process and improve the overall quality of cardiac imaging.
That's a fantastic notion.
Yeah.
What else have you got?
Okay, another thought I had relates to those random ultrasound images they included in the CACTUS dataset.
The ones that weren't even of the heart.
Yeah, those ones. Remember how we said that was a clever way to teach the AI what to ignore?
Right, to differentiate between relevant and irrelevant data.
Well, what if we took that idea even further?
Okay, I'm intrigued.
What if we trained an AI on a data set that includes not just cardiac ultrasound, but a whole variety of ultrasound images?
Like from different organs, different types of artifacts, maybe even images from completely different domains.
Exactly. The goal wouldn't be to classify all those images in detail.
So not saying that's a liver or that's a kidney.
Right. The goal would be to give the AI a really strong sense of what's normal in a cardiac ultrasound.
Okay, I see where you're going with this. So anything that deviates from that normal gets flagged.
Exactly. It wouldn't matter if the AI could specifically identify the abnormality.
It would just say, hey, something's not right here. Take a closer look.
Precisely. It's like a safety net. It could catch things that might otherwise be missed, even if they don't fit neatly into a predefined category.
That's a powerful idea. It could really change how we approach medical imaging, moving away from just looking for specific known conditions.
It would. It would be more about detecting anomalies, anything that looks out of the ordinary.
It's like teaching the AI to be curious, to say, hey, that's weird. I don't know what it is, but someone should probably take a look.
Exactly. And who knows what kind of new insights or discoveries that could lead to.
I love it. It's a really thought-provoking idea.
And it all stems from this idea of training the AI on a broader, more diverse data set, like they did with those random images in the CACTUS dataset.
That's the beauty of research, isn't it? One idea sparks another, and suddenly you're imagining a whole new world of possibilities.
It is, and it's exciting to think about how these ideas could translate into real-world benefits for patients.
Absolutely. So there you have it, folks. A deep dive into CACTUS, a new AI framework that's pushing the boundaries of cardiac imaging.
And some novel notions about where this kind of research might lead us in the future.
As always, a reminder that these novel notions are just our speculations, our way of exploring the potential of these ideas.
But the research itself, the work these researchers have done, it's solid, it's innovative, and it's definitely worth checking out.
If you want to dive into the technical details, you can find the link to the CACTUS paper in the show notes.
And let us know what you think. What kind of novel notions come to your mind when you think about the future of AI and healthcare?
We always love hearing from you. Thanks for joining us on this deep dive.